In this online lecture, we're going to be looking at polar bonds and polar molecules. Polar bonds are bonds in which the electrons are not shared perfectly, and there's one actually is pulling the electrons towards it a little bit more than the other. And this comes from differences in electronegativity, and we'll see where that trend is in the periodic table. So when we look at a molecule, we can look at one individual bond and the two atoms that are in that individual bond and compare electronegativity and determine whether or not we have a polar bond or a nonpolar bond. But we can also look at the entire molecule and look at how the polarity of the bonds add together in order to say whether or not we have a polar molecule or a nonpolar molecule. So the first thing that we're going to do is look at electronegativity and the trend that we have in the periodic table. Electronegativity is how much an atom pulls on the bonding electrons. So if the nucleus of an atom is really hungry for electrons and it has a real strong pull on electrons, it's going to pull very hard on them. And if it's in a bond with an atom that doesn't have a real strong pull, the electrons tend to shift over there. That pull, how much it's pulling, is called electronegativity. And we have this trend in the for electronegativity that is exactly the same as the trend that we have for the other things, and that is as you go up and as you go over to the right, electronegativity increases. Now, we don't have any electronegativity in the noble gases over here because they don't go in bonds. So the most electronegative atom in the table is fluorine. The closer an atom is to fluorine, the more electronegative it is. There's a little bit of a weirdness with hydrogen. It's not a metal. It's a nonmetal. And if I look at hydrogen, it's on top of this column of metals. And you can see that its electronegativity is very different from the one below. Hydrogen is a nonmetal and undergoes covalent bond with all these nonmetals over here. The trend that I want you to know is the trend in the periodic table, and the one thing about hydrogen is that it's less electronegative than all of the nonmetals over here, except for phosphorus, and you can see phosphorus and hydrogen have the same electronegativity. These are the only bonds that we're going to worry about because we're going to be worrying about covalent bonds and their polarity, and these atoms over here primarily and hydrogen are the ones we're going to be concerned with covalent bonds. So remember the trend in the periodic table, up and over, electronegativity increases, and hydrogen is less polar than any nonmetal except for phosphorus, and it's the same as phosphorus. So now, knowing which atom is more electronegative, you can look at individual bonds. Remember, we only consider two atoms at one time because bonds are always just between two atoms. Now, if I look at a carbon bound to a carbon, they're equal, and they will have the same pull of the electrons in this bond. So it's not like one can pull the electrons away from the other. They're shared equally. Now, your book goes and says that carbon and hydrogen have a nonpolar bond because the electronegativity difference is very small. This electronegativity difference is small, although we will see electronegativity differences this small and consider them to be polar in chemistry. Really, what's more important is whenever we have carbon and hydrogen bound to each other, you have a lot of symmetry in the molecule right there. So the symmetry negates any difference that there might be in electronegativity. So as far as you're concerned, you can either say carbon-hydrogen bonds are nonpolar, and I'm happy with that, or you can say they're very slightly polar because of this difference. It's not a big deal. So what happens in a nonpolar, like between a carbon and a carbon? The electrons are shared equally and they're equally distributed between the two carbons. And we don't have to really worry about a shift in the electron density. But then there's going to be some bonds in which you have one atom that is less electronegative and one's more electronegative. How do we know this if let's say you're taking a test and you look at carbon and oxygen, how is it you're going to know which one's more electronegative? Well, you look at the periodic table, and if you look at the table, you remember up and over to the right is more electronegative. And if you look at the periodic table, you'll find carbon is 2 to the left of oxygen, which is over 2 to the right of carbon. So oxygen is more to the right than carbon. Right now, I would get a periodic table and look at it and find carbon, find oxygen, and verify that you can see because oxygen is more to the right, it is more electronegative. Now, because oxygen is more electronegative, it's going to be pulling electrons onto itself more than the carbon. That means the electrons right here in this bond have shifted over onto the oxygen a little bit. Electrons have negative charge, so a little bit of negative charge builds up. And what we do is we write this del negative to indicate there's a little bit of negative. This little symbol right here that looks like, oh gosh, it looks like a circle with a tail on it, a crooked tail on it, or whatever you want to call it. Some people say it looks like a music note. It's actually the lowercase delta in the Greek alphabet. And this is a symbol that you have in mathematics that means partial. So right here, this delta, but we don't say delta negative, we actually say del negative. This del negative here indicates there's a little bit of negative charge on the oxygen. If I look at the carbon, because the electrons are being pulled over to the oxygen a little bit, that means a little bit of positive charge builds up on the carbon. So there are two ends on this bond, a positive end, a little bit of positive, and a negative end, a little bit of negative. And we say it is a dipole. Dipole means two ends. If I look at this bond, you will see there's another way that we can indicate a dipole, and it's with what we call our vector. There is a positive on the end of the arrow. That means positive is at this end, and the arrow is pointing towards the oxygen, saying that the electrons are being pulled over toward the oxygen. Okay, why does this happen, that we get this dipole? The reason that we get this dipole is that the electrons are not being shared perfectly equally. The oxygen actually is hungrier for electrons than the carbon is, so that what we get is a slight electron buildup on the oxygen, slight electron reduction on the carbon. So the electrons are pulled toward the more electronegative atom. When you go to figure out how to write a dipole on a bond, what you do is you find one atom in the periodic table, then you find the other, and then you determine which one is more electronegative. Now, if it turns out that they are not where you can obviously figure it out, then you have to open up your book and find the table that has electronegativity values in chapter 3 and look up the numbers. And then you find that the atom that has the larger number is the one that is going to get the del negative on it. The atom that has the smaller number gets a del positive. Okay, if the atoms are very far apart on the periodic table, that the electronegativity differences are really large, and that's when you have an ionic bond. If the atoms are close together, then their electronegativity values do not differ much, and we say they are that the bond is covalent. If I look at something like carbon-oxygen, carbon-nitrogen, oxygen-hydrogen, or nitrogen-hydrogen, I will find that the electronegativity values are significantly different. For instance, carbon has a value of 2.5 and oxygen is 3.5. There's an electronegativity value difference of 1. This is a very polar bond. If I look at carbon and nitrogen, I see that carbon has an electronegativity value of 2.5 and nitrogen 3.0. It is a relatively polar bond. Between oxygen and hydrogen, it's even more polar. 3.5 on oxygen, 2.1 on hydrogen. That's an electronegativity value of 1.4 difference. Nitrogen and hydrogen are 3.0 and 2.1. So this is an electronegativity value difference of 0.9. They're covalent but very polar. Keep in mind that these particular bonds are very polar. We'll use that again. If the atoms are both nonmetals and the bond is covalent, it's considered to be nonpolar if the values are the same, and you can use this little rule of thumb. It's also nonpolar if the electronegativity difference is less than 0.5. Okay? And that's an acceptable thing to state. Not really true. If you were going to be going into chemistry in greater depth, you actually would not consider it to be nonpolar, but don't worry about it. Okay. The polarity of molecules. You now know how to determine the polarity of a bond by looking up the electronegativity. But now we're going to look at groups of bonds that occur in molecules. The polarity of a molecule depends on two things. One, the individual bond polarities. Two, the overall shape of the molecule. And we learned about the overall shape of the molecule with VSEPR. So now we're going to take polarity of the individual bonds and the overall shape, and we're going to put this all together. The shape of the molecule is important because symmetry is important. When I look at an individual bond, you'll have a del negative and a del positive. But if you have a symmetrical molecule, then all the del negatives on the outside are the same. And so it's not like there's one end of the molecule is positive and one end is negative. And that is actually what causes a polar molecule. So there are these little rule of thumbs. Non-polar molecules usually have no non-bonding pairs on the central atom, and the individual bond dipoles cancel. Polar molecules usually have one polar bond. It actually can be two polar bonds, but you will have what you're going to have are non-bonding pairs on the central atom, or what you're going to find is the atoms on the outside that central atom are different. And that gives you individual bond dipoles that don't cancel. So let's look at some examples, and this will be better, easier to understand. It's kind of hard to understand just words. You have to see some things. So if I look, let's look at this one molecule right here. If I look at this one molecule and we just consider bond dipoles, you will see that if you're saying no electronegativity difference or so small electronegativity difference between carbon and hydrogen, you can say there's no bond dipoles here. But carbon and oxygen have a large difference, and this is the way that the dipole exists. Del positive on carbon, del negative on oxygen. So you would see there's a difference in the two sides of the molecule. This side of the molecule is negative, and this side of the molecule would be positive. Even if you did put in a bond dipole for the carbon-hydrogen bonds, where del positive here on hydrogen, del negative on carbon, del positive on hydrogen, del negative on carbon, you would still see this side of the molecule is positive and that side of the molecule is negative. What I like to say, an easy way to look at this, is that if the atoms outside that central atom are different, and you see you have hydrogen on this side, oxygen on this side, that if the atoms on the outside are different, what you have is a polar molecule. Let's look at this molecule. The boron-fluorine bond is very polar. If you look, I believe boron has an electronegativity value of 2, and fluorine has an electronegativity value of 4. That's a huge difference in electronegativity. And so this is an extremely polar bond. Del negative, del negative, del negative, all on the fluorines. And then on the bromine, you've got a del positive. However, even though the individual bonds are very polar, they all kind of like point in opposite directions, and they cancel each other out. So there's no net dipole. But that's kind of hard for you to see. It's much easier for you to see that the boron has no non-bonding pairs on the central atom, and the atoms on the outside are all the same. So if you have no non-bonding pairs on the central atom, and the atoms on the outside are all the same, there's no dipole for the molecule, and we say it's a nonpolar molecule. So here, even though there's no non-bonding pairs on the central atom, the atoms on the outside are different. Here, no non-bonding pairs on the central atom, but the atoms on the outside are the same, so it's nonpolar. It's a nonpolar molecule. Okay, let's look at ammonia. Ammonia has very polar bonds. Del positives on the hydrogen, del negative on the nitrogen. So there's del positive, del positive, del positive. And there are 4 areas of electron density, 1, 2, 3, 4. This non-bonding pair is stuck up at this point on the tetrahedron, and the hydrogens are at the others. So if I just look at the hydrogens and the nitrogen, I can say this is a trigonal pyramidal molecule. And if I look at the dipoles that we have drawn in, the bottom part of this molecule is going to be positive, and the top part of this molecule is negative. So what we find is this is a polar molecule. But let's look at our simple rules. Non-bonding pair on the central atom causes a molecule to be polar. So even though the atoms on the outside are the same, there's a non-bonding pair on the central atom. It throws the molecule into asymmetry so that this side of the molecule is different from this side, and therefore it becomes polar. So you can just, instead of trying to draw in all your dipoles and everything, just look at the molecule and say non-bonding pair on the central atom, poop, it's polar. Okay, now let's look at this one. This one has no non-bonding pairs. This one has carbon-hydrogen bonds, so if you, excuse me, if you want to, you can consider those to have no dipole, or you can write in del positive here, del negative there, and it's small. But the chlorines are pretty polar. The carbon has an electronegativity value of 2.5, and the chlorines are 3.0, so there's a significant difference in electronegativity. As a result, we find that there's del negatives on the chlorine, and there's del positive on the carbon. Because of this, you would find these two bonds point so that we have negatives out here. And even if we go and put in del positive on hydrogen, del negative on carbon, del positive on hydrogen, del negative on carbon, we would see positive on this side, negative on this side. There's a dipole in this molecule because there's a positive side and a negative side. But let's use the simple way. The simple way is we look at the central atom and we say, no non-bonding pairs. Well, now look at the outside of the molecule. The atoms on the outside are different. Well, even if there's no non-bonding pairs, what do we see? The atoms on the outside are different, so it is a polar molecule. Using this rule of thumb with the non-bonding pair on the central atom and the atoms on the outside make it a lot quicker and easier than drawing in all the dipoles and thinking about whether or not they're canceling each other out. Okay, so let's go ahead and I want you to look at all of these molecules and determine, are they polar or not? And go ahead and try to draw in a dipole on each of these bonds and see if you can get it right. Press pause and then resume when you finish the problems. Okay, let's look at this. First one right here. These bonds are polar. Why? Well, phosphorus is to the, well, it's on a catty corner, so you'd have to look up the numbers. Phosphorus has a value of 2.1, and bromine, I believe, has a value of 2.7. So phosphorus has a lower electronegativity than bromine. That means del positive on phosphorus and del negative on bromine. So there is a bond dipole on each of these bonds, each of these phosphorus-bromine bonds. But let's go ahead and look at it the easy way. The easy way, we look at the central atom and we say, is there a non-bonding pair? There is right here. Then I say, okay, there's a non-bonding pair, so it is a polar molecule. Notice the atoms on the outside are all the same, but that doesn't matter. As soon as you have a non-bonding pair on that central atom, it will be a polar molecule. Okay, if I look at this molecule, carbon disulfide, you'll see that these are on a catty corner, so you have to use your book and look up the value. Sulfur has a value of 2.5 and carbon has a value of 2.5. They have identical electronegativity, so the bonds are nonpolar. Now let's look at the molecule. If I look at the molecule, I see the carbon has no non-bonding pairs, and the atoms on the outside are the same. So this molecule is going to be nonpolar also. Okay, is this molecule polar? The carbon-chlorine bond is a polar bond. 2.5 for the carbon, 2.5 for the chlorine. So carbon, because it has a lower electronegativity, gets a del positive, and the chlorine, because it has a higher number, gets a del negative. So now if I look at this, I want to know, is the entire molecule polar or not? So I look at carbon and I see there are no non-bonding pairs on it. Each pair is in a bond with the chlorine. And so it holds that. That is one characteristic that it has that makes it okay to be nonpolar. Then I look at the atoms surrounding the carbon and I see they're all the same. So it has both of the characteristics needed, no non-bonding pair on the central atom, and the atoms on the outside are the same. So the molecule itself is nonpolar. Let's look at sulfur trioxide. Is the sulfur-oxygen bond polar? Well, if you look at the periodic table, oxygen is above sulfur, so oxygen is going to get a del negative, and sulfur is going to get a del positive. Now, if I look at the molecule as a whole, the individual bonds are polar, del positive on sulfur, del negative on oxygen. Now we look to see, is this molecule nonpolar? Look at the sulfur. Are there any non-bonding pairs on the sulfur? All these electrons are in bonds, so there's no non-bonding pairs. Are the atoms on the outside all the same? Yes, they are. Oxygen, oxygen, oxygen. So the molecule is nonpolar. Be sure and do your in-text problems as you read, and do the end of the chapter problems. These ones here are the ones that I have found to be good ones. Be sure and do worksheets posted for this chapter, because the worksheets have problems that are out of order. They're not classified. All these problems up here in the end of chapter problems, those are classified, and so it's very easy to look up how to do them. When you do the worksheets, it's not so easy to look up how to do them, and so you have to kind of figure out what to do, and it's more like what you would have to do on the exam. Be sure and do the online quizzes that we have for this chapter. So they should come available as we cover material.